So what we're about to do today and for the next few weeks is really get into some deep, deep chemistry. Not that we haven't really been there. But up till now, as you know, we've been studying states of matter, we've been studying energy, how temperature affects this, that, and the other thing, how molecules move, blah, blah, bleed, bleed, and a couple of blah, blah, blahs. So now that we've done all of that, and hopefully in your mind you've got a deep-seated love, joy picture of the beauty that is molecules and their interaction with energy. Now that you've got that deep within your inner soul, we can move farther to understanding a little bit more about that. A decent amount of stuff to get here. So what we're going to do is we're going to get to know these guys pretty well. And we talked about this briefly a couple weeks back when we talked about the periodic table and what an atom even is. If you remember right, the atom is this very, very strange thing that inside of the atom there's this big thing in the middle of the atom that we talked about last week. You guys wouldn't have discovered this, and this is called the
atom.
Wait, smaller? Nucleus, that's right. Good. Alright, so the nucleus is in the middle of the atom, right? And then around the nucleus are these things here that are called
Electrons.
Yes, good. So I was going to say that.
No, that's
They're
not.
called the what?
Iron atom.
Well, where do the electrons hang? This one, I'm representing the electrons here, but where do the electrons hang? What do we call them? Shell or orbit. Alright, so it's either the shell or it's the orbit, right? Anybody remember who discovered the orbits?
That person who thinks space.
The person who J.J. Thomson?
J.J. Thomson realized that there were electrons. He discovered the electrons. Who discovered the orbits? Do you remember? One of my favorite science guys. Yes, Bohr. That's right. You did good. Right, good. So Bohr discovered the idea that there were orbits around here. B-O-H-R, Bohr. And there's different. We're going to talk more about that, a lot more about that later today. So we've got the nucleus and we've got the electrons. And what's I just spelled nucleus wrong? N-U-E. There. N-E-U. Champ. At least I'm not spelling yogurt. All right. So what two things are inside the nucleus? Dos thingos. Go, Sophie.
Protons and neutrons.
Good. Some protons and neutrons are in the nucleus. Good. Protons and neutrons are in the nucleus. The electrons are hanging around out here. Good, you guys. If you remember the word pen, you may not need to, but if anybody asks you what three things are in an atom, you remember the word pen, protons, electrons, and neutrons will remind you what three things it is of. So good. Yay! All right, and as Sophie said, these things here are nowhere near here. Remember the video of how big an atom really is, and in reality how small the atom really is? Go ahead.
The atom is mostly made of air.
Yeah, well, air is made of atoms, so it's mostly made of nothing.
Nothing.
It's nothing. It's zero. It's zippo. It's nada.
Nothing.
And other adjectives. All right, so
This is
that means nothing.
the nucleus.
So right. So remember the nucleus is here, and remember like if the nucleus is the size of the BB, the first orbit is like 2,000 feet away from that. If the nucleus is the size of a golf ball, the electrons are 1.5 miles away from that. So it's cray-cray distances between that teeny tiny little nucleus and the first orbit. And that's just the first, as we'll find out today. There's 7 in there. Go ahead.
Can you weigh atoms?
You can weigh atoms, as a matter of fact. Atoms will have an atomic mass, which we shall also discuss later in the day. Go ahead.
About the periodic table, why does it say 1, 2, 3, 4, 3?
I will tell you about that probably next time we get together. I almost said next week. All right. But this shall count. These actually you've discovered, by the way. This is basically the secret to the universe. Right there. The reason your nose is the way it is, the reason your hair, the reason the water, the reason the folder, the reason the table is the way it is the magical number 1, 2, 3, 4, 3, 2, 1, 0. The magical number right there. So good. All right. So that's basically that. Now, let me erase this for a second. Hopefully this is reviewed. This next thing I'm about to tell you hopefully is reviewed too, but it's good review because we didn't spend a whole lot of time on this. And that's this. So, that's what the atom looks like. These here are the 118 different elements in the universe, and really there's only about 90 some real natural elements in the universe. These guys over here that are beyond, really beyond uranium, are things that some scientists in some labs somewhere smashed two things together and made a bigger atom. So these guys. Everybody else is basically 90-ish normal atoms in And of those 90 normal atoms, most of them are exceedingly rare or are relatively useless. The ones that are really, really useful are, remember it, C, H, O, N, C, right?
Chunks.
Chunk, exactly. Remember chunks. So good. Go ahead.
Actually, it's 97 natural. Or not 97, sorry, 87.
Yes, right. Depends a little bit about how you look at that. But yes, good. All right. So nice. So let us explore the inner workings
Of the universe.
of the atom. So each one of these clever little boxes tell us all kinds of wonderful, fun stuff about the atom. And if you can read it, you're like a genius.
Like you.
All right. I think you overestimated me a little bit. All right, good. So let's learn how to read this thing. And I told you this a little bit ago, but let's review. So let's take a look, for example, at atomic carbon. All right. So carbon. So everything on the periodic table has its cute little box, right? And in its cute little box, depending on the periodic table you're looking at, there's a variety of things. There's a variety of things in the cute little box. On this periodic table, and in most periodic tables, we've got a 6, and we've got a 12.01. 1. Okay? Now, in your notes, if you don't already have this, this 6 represents the atomic number. The atomic number is very important.
Wait, show where it is.
What?
1, 2, 3, 4. Oh, look.
Shows where it is, shows a lot more about it too. And you notice on this periodic table, the periodic table might be the atomic numbers at the upper left. I wrote it in the upper right. Sometimes it's right smack down in the middle. It just depends on the table. But usually it's up here. It's up there. Go ahead.
I just realized that 6 plus 6 is 12, and then if you look at nitrogen, oxygen, and fluorine, it's double the amount of the number.
Good for you. Yeah, I thought it did. And you learned something, right? That's true. Very good. All right, so
Did they do that?
6 is the atomic number. Down here, some clever young person earlier today asked, can you weigh an atom? The answer is, you bet you can, right? In fact, they were weighing atoms before they even knew what atoms were, to be honest, but they were figuring this out a long time ago. This is what's called the atomic mass, or atomic weight. It can go either way. All right. Now, with this here, you can learn so much about the world around you.
Okay.
All right. So, now, atomic number is the number of, anybody remember? Number what?
Atoms.
17.
Good, apparently not. All right. Do you remember?
It's the number of particles.
Ooh, close. Starts with a P.
Electrons.
And it's in protons. Good, it's the number of protons.
Starts with a P. Electrons is not starts with a P.
All right. The atomic number is the number of protons in the atom. And that will never change. The number here is kind of like your social security number. I don't know if you guys know what that means necessarily, but each and every one of you, thanks to the United States government, has provided you with a social security number that is yours and only yours. Nobody has that same number, right? So, garbage. So what is yours? It's like a fingerprint, right? It's your number. It's like your retinal scan. It's your number. You're going to use it for many things, and so will perhaps other people. So, the atomic number is the number of protons. So, that's your number. When it comes to atoms, this is their social security number. They're not very intelligent. They can't remember too many numbers, so they have to keep them simple, right? Not true. But basically, that is what determines that. Carbon will always be 6. Silicon, always 14. Thorium, Thorium, always 107, all right? With the fermiums on here, too, somewhere. See where is that so cool? Oh, here's the guy that did the x-rays.
Yeah.
Where's your thorium and 104?
104? No. Yes, Richard Fourier, there he is. All right, so neat. Most of these names are in Latin, some are in Greek, some are in a combination of both. Anyway, so atomic number is the number of protons in in the atom. That will never ever change. Put this on your too. That will not. Look at the capital letters, right? Okay. Underline it. Not. All right. Change. Ever. If the number changes, the atom changes. If it isn't 6, if it's 7, it isn't carbon, nitrogen. Right? Change. All right. All right. So. All right.
I think somebody had too much coffee.
Go ahead.
There's boron and there's also boronium.
That's right, which makes it so confusing. There's boron, there's beryllium, and there's barium.
There's barium and then there's borium.
Barium? Yeah. And there's borium? Goodness gracious, yeah. Yeah, so it's not easy. There's
What
a lot
about
of-
boron?
There's boron, that's right. Boron is...
Boron, 5.
Where'd you go?
There's also bromine. 3. There's also bromine and bismuth.
I know, that's all kinds of stuff. Go ahead.
What does it mean by unknown where it's saying?
RF. And then
Where?
Well, no, it's saying like if
This
it's
one?
black, it means it's a solid. If the
Okay.
number's black, if it's blue, it's a liquid.
Unknown means it exists for such a small amount of time, and we've never made more than like 1 or 2 or 10 of them at a time. They don't even have time to form a normal state before they disappear off the planet. So if we can make like a bazillion of them, then maybe we can see if these are solids or liquids or gases. But since we can only make 10 and they disappear less than a snap of a finger later, we have no idea what their normal states are.
So then why are they even elements? If they only exist for the purpose of...
They're fun. It's fun to throw them on there, see what happens. Kind of gliding things together, see what happens. It's really kind of how that works. All right, so, good question. So, okay, where were we? Okay, so the atomic number is the number of atoms, the number of protons. That will not change. That will always be the same. All right, now, let me erase this for a second. All right, the atomic mass. Atomic mass is the number of protons. Protons, you just said that was atomic mass. Atomic number. How can it be atomic mass too? It's the protons and, oh, and there's an and. I shouldn't have talked so soon. There's an and. And neutrons. In an atom. Oops, good job. So the atomic number is the protons and the neutrons. Remember, the neutrons weren't discovered until 1953 or something like that. The atomic mass is the number of protons and neutrons.
You need
Atomic-
to put an A to an and. 'Cause there's,
Need to what?
you need to
Oh, you're right.
Again, this is why I'm not...
That's right.
You told us it's proposed.
So the quiz question is science gym.
Your next about yogurt science gym.
Doesn't have to be English teacher. Doesn't have to be English gym. I have to talk like that too, which isn't an English accent. All right, so moving on. So the atomic mass is the number of protons and neutrons in an atom. So you may be asking yourself, how do I know how many neutrons is in an atom? That's an excellent question. Turns out it's very simple to know. It's what we like to call, and even simpler, it's what we like to call subtraction.
I don't think that's that coffee.
So in this case, I'm trying to make this as exciting as possible. So in this case, if the atomic number here is 12, right? If the atomic number is 12.011, and we want to find out how many protons and neutrons are in here, I subtract 12, I subtract 6 from 12, and that equals 6.011. Good. So that's how many neutrons are in here. Now, you should be thinking to yourself, how, if protons are just like a teeny weeny little single particle, and neutrons are a teeny weeny little single particle, how can I have a 0.0011 of a neutron? It's like having a 0.011 of a shoe. I mean, that doesn't make any sense, right? It's like, or when you do the average the nuclear family has 2 kids, has like 2 parents and 2.5 kids. So where's that half a kid? It's supposed to be running around and everybody's having the lower half or the upper half? Or the right half or the left? I don't know. So anyway, the reason why this is here is that's the average. That's the average. So if we took all the carbon atoms in the universe and we averaged them all out, it turned out some of them weigh more than 12. A couple, a few, not many, but some of them weigh more than 12. So for example, you guys can go home tonight, you can tell your moms and dads and other people who may be wandering around your house, call the police if necessary. So you can tell these people, look, I'm above average. Okay, so you can tell your parents that I'm above average, and they'll say, really? Actually, they won't say really, they'll say, we know you are. So, but you can say, no, we're really above average. And you can say, how are you above average? And you'll say, because I've got an above average number of eyeballs. I'm above average. Because, right, there are people out there with only 1 eye. There are people out there with no eyes. You have 2 eyes. There's nobody with 3 eyes, so you're above average eyeballs.
Take who you are.
Exactly, yeah. You have an above average number of nostrils. You have an above average number of elbows, right? You're above average. You're amazing.
Belly buttons.
Above average number of toes. That's right.
So an above average number of belly buttons.
So, that's right. Well, I don't know. I think everybody's got at least one belly button unless we go way back in time. But yeah, okay, so.
People still walk around.
Yeah.
A couple other people may be there. But, so, where was it? Okay, so that's why it's 0.011, because that's an average. These are the averages. So for you guys, don't be worrying about, like, oh, dude, that's like weird math with decimals and stuff. Don't worry about this part, right? When I ask you guys, hey, how much the atomic weight of carbon? You can look at carbon and go, 12. Done. Then these 0.011s or nothing like that, right? Just give me a 12, because that's fine. So how many neutrons are there? 6. That's it. There's 6 neutrons or anything when you're done. Because you can't have a 0.011. That's kind of serious. The atomic mass is the number of neutrons in an atom. So, let me do a quick review. Let me make sure you guys got this straight. We'll erase this for now. Wink, wink. Okay. So let's say, for example, I guess I'll leave this here. Let's say, for example, we've got magnesium. How many protons are in magnesium, and how many neutrons are in magnesium?
305.
So we have magnesium. How many protons and how many neutrons?
24 neutrons
No points.
and 12
Just can't have a point.
protons.
So we've got atomic mass of magnesium is, atomic number of magnesium is 12. So it has 12 protons. I'll just put a P here. Its atomic mass is 24. So I'm going to AM. Do a little subtraction here, and I get 12 neutrons for its neutrons, right? Fairly simple. All right, let's do it. Don't say it out loud. Let everybody have a chance to think about this for a second. Let's go a little bit bigger. What about cobalt? Cobalt. Don't say it out loud.
Okay.
Let everybody have a chance to look at this. What about cobalt? And I would recommend for those of you guys who are note takers, put this in your notes so you have a reference to this later when you're trying to study this and remember how this works.
I'm around.
Wait.
Right. So we got cobalt, which is atomic number 27.
What are we putting in our notes?
So just write this down. So if you've got cobalt, its atomic number is equal to 27. Right. So how many protons does it have? Question.
So wait, the protons is the atomic number?
The protons are its atomic number. So here's cobalt.
So what's the AM for?
Atomic number.
Okay, Gina.
So its atomic number is 27. How How many protons does it have? How many neutrons does it have? Its atomic mass is,
58.923.
So just 59.
yeah, round that. If you don't on quizzes, I'm not going to take off. If you put 58, I'm going to say fine, no big deal. But really, you should round it. It's almost 59, so round it to 59. But again, I'm not going to take off if you blow that. So its atomic mass, AM, is equal to 59. 59. There we go. Now, how many P's, how many N's? Do. All right, anybody ready for the answer? Let's try. How many P's? Sean, how many P's?
27.
27 P's. It's right here. One of the easiest questions in the universe. What color is blue? Blue. Yes, that is correct. So that's basically it. So the number of protons is indeed that number. It's right there. Neutrons is a little bit harder. How many neutrons? Go.
32.
Yeah. And you know that because you're a mathematical genius. You have taken 59. Atomic mass is the number of neutrons and the number of protons. So if I know I've got 27 protons, I do a little math, and I get 32.
Yogurt, white.
32. So, make sure you get this, because with these lower ones, like you were saying, Annabelle, you notice that these basically just kind of double. And a lot of the lower ones do that. So you're going to see that they're the same all the way across. But you can't bet that that's going to be true. So be sure to check that that's true. Even Beryllium breaks it. Actually, look at the way it is. So, all right. So good. So, all right. So that feel good? You guys got that? All right. Now, I'm going to give you a little something else. All right. Because unfortunately, it's not that easy. No. So, I'm sure you were asking yourself, I'm sure you're asking yourself, well, wait a minute. If normally cobalt has 59, who are these little mutants out there with less than 59? Apparently there must be a couple with like 58, or maybe even 57. I don't know, I'm just making this up. So who are those guys? Don't they all have 59? Nay, some have less, like I was saying, even above average number of eyeballs, blah, blah, blah. So that's true. So that means there must be atoms out there with an unusual number of neutrons.
700.
And we call that something. We call that an isotope.
Did you spell
Are
that
there
right?
any isotopes?
So an isotope is an atom. Notice the N part. An atom with this W with a slash, that's just kind of shorthand for with. So I'll start doing that. An atom with an unusual number of neutrons. So an isotope is an atom with an unusual number of neutrons. Neutrons.
Yep.
Dig it. Yo.
Spelling classes.
So, if I had, so let's say, for the notes, if you have carbon with an atomic mass of 14, how many atoms? How many neutrons? If they're covered with an atomic mass of 14, how many neutrons do you have? Don't say it out loud. Let everybody think what happens next. If they're covered with an atomic mass of 14, how many neutrons do they have? That's a how. If they're covered with an atomic mass of 14, okay, anyone want to try it? Simple math, go ahead. Sean, give it a go. Yeah, right. So it's normally, if it's atomic mass of 14, I take 14 minus 6 and I get the answer 8. Is that the normal number?
No.
Actually, it's not that unusual. This is what's, if you've ever heard of carbon dating, they're looking for this isotope of carbon. Carbon 14, carbon dating. Yeah, it's what chemists do when they really get bored, they go carbon dating. All right, so, okay, moving on. Bad boy. All right, so if you have a carbon with an atomic mass of 14, how many neutrons do you have? You have 8 neutrons. This is what would be considered an unusual number of neutrons. So you would call this an isotope of carbon. Right? Because it's unusual. You'd be like, that's unusual. Right, exactly. All right, good, you guys. So that's the atomic number. That's the atomic mass. All right, good. And that's an isotope. All right. So let me give you a quick problem here. So the problem is, if you have an isotope of calcium, how many neutrons do you have? Here's calcium. If you have an isotope, don't say it out loud. If you have an isotope of calcium, put it in your note there, note taker. How many neutrons do you have? Remember, an isotope is an unusual number of neutrons. So this is perhaps the second easiest question of all time. It's not quite as easy as what color is blue? Blue.
Carbon.
But it's pretty easy.
Carbon.
If you get it. If you don't get it, it's going to be easy once you understand it. Might not understand it. Does anybody have a guess?
Wait.
So it's got, what's an unusual number of neutrons for calcium?
Any unusual number?
Yes.
Yeah.
Would it be?
There's only one wrong answer to this.
Oh, 19?
Yeah.
Okay.
It's supposed to have 20, right? It should have 20. That's the usual number. Well, it's an isotope, so it's unusual.
Yeah, if you have
19, 21, 2004, 2, negative 5, 18. Actually, negative would get a little twisted. But basically, there's only one wrong answer, and that's 20. So it's like the question, what color is not blue? Orange, pink. There's only one wrong answer, and it's blue. Exactly. Right. So this is the same thing. What's the normal number of isotopes for calcium? It should be 20. If this is an isotope, that means it's anything but anything but. Now, officially, they don't get that crazy. Usually there's 1 or 2 more protons, or 1 or 2 more neutrons,
What's
1 or 2
the
less
record?
neutrons. I'm not really sure, but it's probably some of these bigger fellers down here where you've got to get some more nutty neutron ratios. That's that. Now, you're thinking to yourself, gosh, we've done protons and neutrons. I hope we do electrons. Because that's the extra. How do we count? What are electrons? Well, here, dreams have come true.
Yay!
Science Jim, also known as Science Santa Claus. All right, so how many electrons are there in an atom?
A lot.
All right, this is relatively easy. If there are, let's take carbon again. If carbon is atomic number equals 6, number of protons equals 6,
Yeah.
number of electrons equals
6,
6.
7.
That's so awesome.
Wait.
It's the same thing. It's the same thing.
That's
as
the easiest question in the world.
That's, yeah, it's up there. It's going to get harder in a second, but that's the easiest question in the world.
Okay, never mind.
Easiest question.
So, the reason for this
Statement.
is because nature likes to be neutral. Nature likes to be totally neutral, man. So, that means the protons have a charge. Anybody remember the charge the protons have?
Positive?
Master charge. Yes, it's
Pro. Yeah. Pro, positive.
pro-positive. Good, you got it. Pro-positive, proactive, got a D. Which means electrons have to be negativo. Which means if you've got certain pluses, you got to have that many minuses to be 0. You want it to equal to 0. And then when it's 0, it's a neutral atom. Go ahead.
So that means the electrons will always equal the neutrons?
No. Because I'm going to make it more complicated in a second. The electrons will always equal the protons. Not necessarily the neutrons at all. Neutrons are a separate beastie. But they will always equal the neutrons. They will always equal the protons. Unless There's an unusual number of electrons. So there can be an unusual number of protons and electrons. Okay, let me check this out. All right, so here's the deal. So protons are always going to do that. So before we get to that for a second, let me ask you very quickly, and feel free to shout it out, perhaps out of the top of your lungs. How many electrons is in a normal atom of tungsten? How many electrons? How many electrons is in a normal atom of tungsten? 74. How many electrons are in a normal atom of copper? 29. How many atoms are in a normal atom of manganese?
25. None.
That's the thing. That's correct. Good. But now, we need to take it up a notch. Taking it up a notch. Well, kind of. All right, now we're going to go to, and this is a little bit tricky. We're going to get to ion. Ion is an
Lithium-ion battery.
atom, that's true, with an unusual, lots of N's in this lecture, an unusual, this is an unusual number of
Electrons.
Electrons.
Suckers.
there's an unusual number of electrons. That would be an ion. Okay. Now this is where this gets just a little bit, because for you to know what kind of an ion it is, we say that there's a charge on the atom. You can also say, also it is a charged atom. How do you keep a rhinoceros from charging? You take away its credit card. How do you keep a rhinoceros from charging? You take away its credit card so it can't charge anything? Alright.
That is unworthy of me.
Alright, so good. So an ion is an atom with an unusual number of electrons with a charged atom. So this makes this a little bit trickier. With neutrons, we just know there's this many neutrons, there's that many neutrons in the isotope, blah, blah, blah. In this case, we're going to have an ion be like +1, -2, +3, -1. So it gets a little bit trickier. And here's why. It's because electrons have a charge. They have a negative charge. So you can have an atom with more electrons than normal, or less electrons than normal. If you have that, you have a charge. So let me give you an example, again using our old friend. Oh, he's my friend. He should be your friend, too. All right, so carbon has how many protons?
100.
I think you're going to get how many protons in carbon by memorization. How many protons? 6. So what is this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that represents the number of protons, right? 6 proton particles, 6 little bitty balls that are all positive signs. Now, we're going to also put in here some electrons. How many electrons do they normally have? Does carbon normally have? It's not an ion, it's a normal stable molecule. 6 it is. Boom, chicka, boom, chicka, boom, chicka, boom, chicka, boom, chicka, boom. 6 it is, all right?
You're looking at a battery.
Now the deal is that these guys are, actually you are, these guys balance each other out. They've all got dance partners, right? You dance with me? Well, sure, I'd be happy to. So all these guys have dance partners. Shoot. So their overall charge is 0. They all cancel each other out. That's a normal atom.
Oh no.
But let's get to ions, shall we? Let's say I've got a situation where I've still got 6 protons. 1, 2, 3, 4, 5, 6. Will I ever have an atom of carbon that has more or less than 6 protons?
Yes. Yeah.
Starts with an N, ends in an O. No, I will never, 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 never. If it's carbon, it will always have 6 because this is its social security number. If it has 7, it's no longer carbon, it's nitrogen. If it has 5, it's no longer carbon. Boron, right?
Not boreal.
So carbon will always have 6. Always. All right. Now, let's say I have an ion of carbon. I have an unusual number of electrons. So let's say I've only got that many electrons. Ooh. What? So in this case, what happens here? These guys cancel out. These guys, however, are left without dance partners. They're standing in the corner of the room, just staring at each other going, I didn't really want to dance anyway. All right, so this is how our graph's going on there. So what's the charge on this atom?
2. Dose.
Positive dose. Right.
Dosey.
So it's a +2 ion.
That's the dance they're doing.
Now we can use it the other way too. What if we have it this way? What if we have another carbon? 1, 2, 3, 4, 5, 6. But this time, oops.
You have 3. That's a lot of negatives. Someone here is very negative.
What's the charge on this? Officer?
3. 3, that's negative.
No, it's 2. 2. It's 2. Everything 2.
2.
Oh,
Zinc,
cute.
zinc, 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 zinc. It does look like a 3 because I messed that up a
Why
little
do you
bit.
write this down?
This guy.
Be sure to know it. So this is -2.
I just won't write it down because I'm bad at remembering things.
So if you've got an atom with more electrons than usual, it's negative. If you've got an atom with less electrons than usual, it's positive.